So in this installment, we will build on the previous two. So now we have changing velocity with a non-zero initial velocity. So we have the same jogger running at 5 meters per second, but she also accelerates. So we have an acceleration of 1. That looks familiar. Acceleration 1, 1, 1, 1, 1, 1, 1, 1. Constant acceleration. And the velocity in the beginning is 5. And after 1 second would be 6, 7, 8, 9, 10, 11, 12. So then the average velocity becomes average of 5 and 6 is 5.5. The average of 5 and 7 is 6. The average of 5 and 8 is 6.5. Average of 5 and 9 is 7.0. Average of 5 and 10 is 7.5. 5 and 11 is 8.0. And 5 and 12 is 8.5. And I know we did that quickly, but 5 plus 12 is 17 divided by 2 is 8.5. So then the delta x is v bar multiplied by t. And so that would be 0 displacement, and then we have 5.5 and 12.0 and 18, 19.5 and 28.0 and 37.5 and 48.0, and this is 59.5. So if we plot our displacements here, we start at 0, and then we're at 5.5, and then we are at 12, and then 19.5, and then 28, 37.5, 48.0, and 59.5. So what we can see is the delta x in equal time intervals is increasing. Delta t's are equal, but delta x is larger, so this velocity is increasing. Now, what does this graph look like? Well, here's our VT, and we have velocity that ranges up to 8, and time that ranges to 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Like so. So at time 0, we have a velocity that is equal to 5. Oops, is there. Excuse me. And at time 1, we have a velocity equal to 6. Oh, I scaled this incorrectly, didn't I? I looked at the average velocities instead of the instantaneous velocity, which is what we needed. So 3, 6, 9, 12, and there's our v. So at time 0, we have a velocity of 5, about there. And then at time 1, we have a velocity of 6. And then at time 2, we have a velocity of 7. Time 3, we have a velocity of 8. Time 4, we have a velocity of 9. 5, we have a velocity of 10. 6, we have a velocity of 11. And 7, we have a velocity of 12. So that is our VT graph. Now the origin is set to 0, 0. Y-axis is velocity, x-axis is time. The things we will read off the graph are velocity and time. The slope, delta v over delta t, is acceleration, and the area is v delta t. Meters per second times seconds is meter, and that is the displacement. So what we notice then, in the first second, we have an area of 5.5. And in the next second, we add 6.5, bringing us up to a total of 12. And in the next, we add 7.5, bringing us up to a total of 19.5. And so on and so forth. Well, if we want to find this velocity, or find the area, this, curiously enough, traces out the shape of a trapezoid. And the area of a trapezoid is 1/2 b1 plus b2 times the height. Now visualizing this means that this must be the height, and this is base 1, and this is base 2. The average of base 1 and base 2 actually would put us here at this midpoint. So what it's doing is taking this area and putting it here. Effectively, the area of a trapezoid formula turns a trapezoid into a rectangle. So that's what we're doing there. All right, so now 1/2 base 1. Base 1, well, let's call this base 1. Well, that is V0. And base 2 is the velocity. And the height is t. And that is going to be our displacement. Now, v, this instantaneous v, is a variable. And that v is described by a straight line. The y-axis is v, the x-axis is t, the y-intercept is v0, and the slope is the acceleration. So v equals at plus v0. Oh my gosh, that's where that formula comes from. So, whoa, we have, let's distribute these. We have 1/2 v0 plus 1/2 v, and all of those are going to be multiplied by t. So 1/2 v0t plus 1/2 vt. But v is at plus v0. So 1/2 at plus v0 times t. Going further, and we'll bring this up over here, we have a delta x, which is equal to 1/2 v0t. And now we'll distribute the t first, which will make this at squared and this v0t, and then there'll be a 1/2. So we have 1/2 at squared plus 1/2 v0t. Now, we'll pull these terms out, 1/2 at squared. You notice we have 1/2 v0t plus 1/2 v0t, which is v0t. Oh, so the displacement is 1/2 at squared plus v0t. And we know delta x is x minus x0. And so adding xo to both sides, we end up with x equal to 1/2 at squared plus v0t plus x0. And that should come as no surprise that that is the other formula that we are supposed to know, the other relationship we're supposed to know. From the previous example, we had x equals 1/2 at squared plus xo. And we also had x equals v0t plus xo. And this was for constant velocity. This was for constant acceleration with v0 equal to 0. And this is with constant acceleration v0 not equal to 0. So it looks like we should have 3 different formulas for the instantaneous position. But let's suppose, for example, that the initial velocity is 0. Well, then this term would drop out, and we are left with this. Let's suppose the acceleration is 0. Then we are left with these two. So we only need one equation to rule them all. It does require constant acceleration, but it will solve every problem, whether or not there's acceleration or whether or not there's initial velocity. And that's why we only need that one formula. Now, just jumping back, one last thing to the instantaneous position. What do we do, of course, if we want the position? Well, we add the initial position to delta x. And so if this jogger hadn't started at 0, but instead started at 8, we would add 8. 13.5 and 20 and 27.5 and 36 and 45.5 and 56.0 and 67.5. And again, all of those points would be shifted by 8. A shift of 8. What you will often see is people using the formula delta x equals 1/2 at squared plus v0t with no x0. And they just deal in displacements. But remember, delta x is x minus x0. And so if we add x0 to both sides, we end up with a formula that will give us the actual instantaneous position as opposed to what the change is. So whenever we have a displacement, we can find the initial position by adding, we can find the instantaneous position by simply adding in the initial position.